Oh, hello, everybody. Welcome to our monthly seminar. So today we have the pleasure to have with us Jiaxing Zhao, talking about electromagnetic fields evolution and detection in relativistic heavy-ion collisions. His work together with his collaborators from China and Germany was one of the APS highlights a few months ago. So it's very interesting to have you talking to us and listening from the source. So let me briefly introduce our speaker. So Jiaxing Zhao obtained his PhD under the supervision of Professor Peng Phase Wang from Tsinghua University in 2020. After that, he stayed in Tsinghua to do a postdoctoral research. And currently, he's at Subatech in Nantes, in France. His research focuses on heavy flavor hadrons, in particular, heavy flavor exotic hadrons production and electromagnetic fields in high energy nuclear collisions. So thank you very much for accepting our invitation, and please go ahead.
Okay. So, good afternoon, everyone. So first, let me thank the organizer to invite me for this talk. And I'm very glad to be here for this talk and to present our recent study about electromagnetic field evolution and the detection in relativistic heavy-ion collisions. And this topic is mainly based on these 4 papers. So this is the outline of this talk, and first I will give a brief introduction about the electromagnetic field created in the heavy-ion collisions and the related studies. And next, I will show our study about the electromagnetic field evolution in the early stage of the heavy-ion collisions, such as pre-equilibrium stage. And then I will show the new phenomena we proposed to name the incomplete electromagnetic response of hot QCD matter, and finally, I will give a brief introduction about the electromagnetic field influence on the heavy flavor probes. And at the end of this talk, a small summary will be given. So we know in the non-central heavy-ion collisions, a global magnetic field is generated via the relativity potential of the 2 charged nuclei, as shown in these cartoons, and those, maybe I can find them, and those theoretical works. The magnitude of the electromagnetic field depends on the colliding energies and the impact parameters, while the maximum of the magnetic field can reach 5 MPa in go-go collision, in semicentral go-go collisions at RIC, and almost 70 MPa in semicentral net collision center C. So this is the strongest magnetic field created. And those figures show the different components of the electromagnetic field. You can find the detailed description in our recent review papers. So such strong electromagnetic fields attract much more attentions. Like first one is, as shown here, we can see the Carroll condensate may increase with the magnetic field and no temperature, and the Carroll condensate may decrease with the increase the magnetic field and high temperature, which is also known as magnetic cathonosis and inverse magnetic cathonosis. So that means the strong magnetic field will affect the QCD symmetry and the QCD phase structure. The second one is experimentally, the strong electromagnetic field may give rise to searching for the fantastic phenomena such as Carroll magnetic effects in the Carroll unbalanced system. The magnetic field may drive the topological charge fluctuation into a global electron charge separation. This can be observed in the experiment. However, after many years' efforts and also the isobar collisions, the existence of CME is still under control. It is as controversial means that. The third one is the electromagnetic field induced photon production, such as photon-produced gypsum and photon-produced dileptons, which has been observed in the experiment, as shown here, the result from Alice and from Rick. The first one is the electromagnetic field may give rise to the splitting of the directive flow of D and D mesons, which also observed in the experiment as shown here. And the last one is in the strong electromagnetic field, the static properties of trimoning may be changed, and the evolution and their dynamic evolution in the heavy-ion collisions may also change in the strong electromagnetic field. And those the figures show the trimoning mass will be changed in the magnetic field, and the shape of trimoning will also change and becomes anisotropic. You can see those reference for the detail. So those electromagnetic field related effects rely both on the stress and the lifetime of the electromagnetic field. Well, after the collisions, the spectator will moving forward and backward with the same rapidity, but the participant will lose rapidity due to the collisions, and the magnetic field created in the central region will decrease from its maximum value as shown in these figures. We can see here, the dashed line is the contribution from the spectator, while the dotted line is from the participant. We can see the spectator each contribute a lot in the very beginning of the heavy-ion collisions, while the participant will contribute at a later time, where the stress of the magnetic field is almost three orders smaller. So from this we can see, if we do consider the charge, the quark plasma produced in the heavy-ion collisions, that means in the vacuum, the electromagnetic field will decrease fastly, and which lifetime is smaller than 0.2 Fermi over C in vacuum at RIC, and it will be much shorter at HC. But people propose that the created of quark plasma in the heavy-ion collisions will deny the decay of the magnetic field due to the electromagnetic response. But this depends on the electronic conductivity of the QGP matter, and further considering the expansion of the QGP matter, we need to employ the magnetohydrodynamics. But considering those, the various theoretical model give very different lifetime and the stress of the magnetic field, and showing these two figures you can see here is very large difference. So this give us the opportunity to study the electromagnetic field evolution dynamically in the heavy-ion collisions. And now I come to our study for the electromagnetic field evolution in the very early stage in the heavy-ion collisions. That means the pre-equilibrium stage. So here, this cartoon shows a timeline of heavy-ion collisions, and after the collision, the system undergoes a pre-equilibrium stage, and after the pre-equilibrium stage, the system becomes local thermalization, and it becomes the QGP stage. And with expanding the temperature and the energy density of the QGP will decrease. And when the temperature is lower than the critical temperature, the quark and the gluons will convert to the colorless hadrons again. So here, the pre-equilibrium stage is almost appear less than 1 Fermi, and which is far from equilibrium and gluon-dominated system. And The pattern distribution function, which measured from the deep inelastic scattering, tell us the gluon-dominant and very small s region, and with the x decrease, the contribution increase. But this enhancement will reach a maximum and form a state named color glass condensate. This color glass condensate can be the initial stage of the heavy-ion collisions. And after a time tau, the gluon fields will converge to the unshared particles, and which can be described by the kinetic theory, as we use the bumps here. So bumps is the Monte Carlo method to solve the Boltzmann equation numerically, and which is developed by Zhao and Casgrena firstly. And here in the electromagnetic field, we need to consider the Lorentz force here. And here, the right-hand side is collisional terms, that 2 scattering and 2 scattering process. And in the Monte Carlo method, the collision probability of 2 particles in a spatial cell delta V and within a time step delta T can be given by this formula. And here, the test particle technique is introduced to reduce the fluctuations. So in our study, we consider only the 2-2 scattering process, and we consider all possible 2-2 process channel here, like gluon to gluon and gluon to quark, antiquark, and so on. Here, the cross section is given by the perturbative QCD, and we also include the device screen mass for gluons and the thermal quark mass for the quarks in the hot medium, as shown here. So now, aim to evolve the Boltzmann equation, we need the initial condition. Here, we consider that the initial state is full of gluons. It's only gluons, and which momentum space can be sampled by the CGC model, while for the coordinate space, which is controlled by the global model. And after the collision, after the inelastic scattering, the quark and antiquark will be produced gradually. And shown in this figure, we can see the number of quark and antiquark is increased gradually. And the gluons will traverse to the thermalization smoothly via the elastic scattering, like gluon to gluon. But the gluon is not carry the charge. So gluon will not respond to the electromagnetic field, and only quark can respond to the electromagnetic field. So when the quark produced, they will feel the Lorentz force and moving in the system, and their moving will generate the electromagnetic field via the Dirac potential, as we all know. So here, this figure shows the total magnetic field and the induced magnetic field. Here, the black line is a vacuum case, and while the red line, blue line is considering the pre-equilibrium stage evolution. And we can see, because the number of the quark in the initial stage is very small, so it's very difficult to generate a strong induced magnetic field. So the evolution of the total magnetic field at T smaller than 0.4 from UVC is almost same as vacuum. That means the magnetic field evolution in the pre-equilibrium stage is almost same as the vacuum. And our study is almost same as others. So this is the first dynamical description of the electromagnetic field evolution in the pre-equilibrium stage. And now we come to the new idea about the incomplete electromagnetic response of the hot QCD matter. To begin this, let me introduce the electromagnetic induction. That means a change in B field, magnetic field, will induce the E field, and this E field will generate a Faraday current in the coil, and this this current will create a B field which direction is opposite to the changing of the external magnetic field. That also names the Lenz's law. While in the general case, this electromagnetic induction can be included in the Maxwell equation. So here, the current is related to the electromagnetic field via the Ohm's law. That's what we are familiar with. But we challenge the Ohm's law in hot QCD medium. The idea is here is it needs some time for the current electric current to build from 0 to the Ohm's law value. And if this realization time is larger than the lifetime of the external magnetic field, so the lower than expected electric current will suppress the induced magnetic field. And this will make the electric response incomplete. So here, the realization time of the induced current can be estimated from this value, this formula. We can see the realization time is proportional to the electronic conductivity and the inverse proportional to the temperature. So usually for the normal case, like conductor or electromagnetic plasma, the realization time of the induced current is much smaller than the lifetime of the B field. In this case, the incomplete electromagnetic response can be neglected safely. While for the strongly interacting QCD medium, such as quark-gluon plasma, the lifetime of the B field is very short. It's even shorter than the realization time of the induced current. So in this case, the incomplete electromagnetic response should be significant. And now, following, we want to realize this idea with dynamic evolutions. So we first to build the system. The system is full of equilibrium gluons and the two flavor quarks and its antiquarks. The momentum distribution is given by the Boltzmann equation, while they are distributed uniformly in the coordinate space, and the temperature of the system is controlled to be a constant equal to 255 MeV, and the scattering cross-section between the quarks is chosen to be a constant value, which equal to 1 of 2 millibars, and the pattern evolution is described by the bumps as I showed before. So first example is we choose a linear decreased magnetic field as shown here. So the advantage of this magnetic field is we can get the induced electric field analytically as shown here. So from the pattern scattering cross section, we can get the electric conductivity, and with this, if the Ohm's law is satisfied, we can get the Ohm law current directly, as shown in this figure with the dashed lines. While in the real case, the pattern evolve is described by the bumps, and the current can be connected via its definition. The results show with a solid line here. We can see the induced electric field generates a curved circular electric current, which is increased with from 0 and relax intervals to the value from the Ohm's law. And from this figure, we can see the realization time is proportional to the electronic conductivity, and so it's inverse proportional to the cross section as shown here. We can see the realization time of the blue line is larger than the red line. So for the magnetic field, if the Ohm's law is satisfied, we can get the induced magnetic field easily, as shown with dashed line here. While for the real case, the electromagnetic field can be obtained by counting all the electromagnetic fields which are generated by the charged quarks in the system, and which result is given by the solid line here. We can see similar to the electric current, the induced magnetic field is increased from 0 and the relaxing intervals to the value calculated by the Ohm's law. And the very small value at the beginning time, which is caused by the incomplete electromagnetic response. Okay, let's see the second example, which is the case of the non-central heavy-ion collisions. So here the two nuclei are replaced by the 2-point particles with the same charge and mass, and they are moving in the z direction with the impact parameter equal to b. And if the Ohm's law is satisfied, the electromagnetic field in the quark plasma can be solved by this Maxwell equation. This equation can be solved analytically, and the solution as shown here, you can find the detail in this Tuchin's paper. So from this, we can see, considering the electronic conductivity, the lifetime of the electromagnetic field, here is only the magnetic field, is largely enhanced. And in this case, the induced current is also can be get easily as shown with dashed line in the left figure, and the induced magnetic and the total magnetic field in the right figure. However, for the real case, as I mentioned before, we need to connect the induced current by the definition and the electromagnetic field generated by all charged particles in the system, and which gives the real value as shown with the solid line here. In both cases, in both figures, we can see the current from the bumps shows almost a 20-fold lower peak than the Ohm's law. So this small induced current will largely suppress the induced magnetic field. So in turn, we can see the total magnetic field is almost decay as vacuum in the beginning time of the system, as shown in the right figure, as you see. So this incomplete electromagnetic response caused by the Ohm's law violation has attracted many attentions. That means even if the quark plasma appears after the heavy-ion collisions, but considering the impact electromagnetic response, the induced magnetic field will also be largely suppressed, and its value should be much smaller than the maximum value. So this may be should very difficulty for the experiment to observe the magnetic related phenomena. And the last one is heavy flavor probes. And we know the heavy quark, their mass is much larger than the lambda QCD. So that means their production can be described by the perturbative QCD, and the number is almost conserved during the evolution. And due to the very large quark mass, they are produced at a very early stage, and which time is even shorter than the lifetime of the B field. So the heavy quark can feel this strong but short-lived electromagnetic field. As for the tremolling, the electromagnetic field will change the device screening and the dynamic dissociation of the tremolling in the hot QCD matter. And our study and with others confirm that the device screening in the magnetic field is increased. And for the tremolling gluon dissociation process, we we solve the QCD multiple expansion. We use the QCD multiple expansion to obtain the ground dissociation cross section of tremoli in the electromagnetic field. Here I just show the result as shown in the right figure, and shown here we can see, considering the tremoli deformation in the magnetic field, the dissociation cross section will divergent at many many points that's corresponding to the Lambda levels. So this so come to the summary. So first, the strong electromagnetic field created in the non-central heavy ion collisions is no doubt is true, but considering the dynamic generation of quarks in the pre-equilibrium stage and the incomplete electromagnetic response of the QCD matter, the electromagnetic field generated in the heavy ion collisions decay faster, and their magnitude will be greatly reduced compared with its maximum value at the beginning time. So we need most sensitive probes, but so and heavy quarks they're produced at the very early stages, so it can be an ideal candidate for this, and it's worth to study. And finally, I want thanks to my collaborators, and thank you for your attention. Thank you.
Thank you. Thank you, Jiaxing, for the very nice seminar. So let me now open for questions. We have here a couple of questions. Malena.
Hi, can you hear me?
Yes.
Hi. So about your conclusions, could you tell us how strongly dependent are your conclusions on two things, on the energy of the collision and also on the way you're calculating the electromagnetic fields? What I mean is on the linear Wishart approach.
So first, you mean our conclusion related to the colliding energy, right?
Yes.
So first, so this conclusion is independent on the colliding energy, because in the high energy or low energy, the system will undergo the pre-equilibrium stage, which is same, right? The quark will generate gradually in both colliding energies. So without quarks, without the induced magnetic field, so that means the evolution of the magnetic field will same as the vacuum case in the pre-equilibrium stage. And for the second, the incomplete electromagnetic response, which is how to say? I think this is kind of depends on the colliding energy, because we know in the very high energy colliding collisions, the lifetime of the B field will be shorter and shorter, right? If the colliding energy is very small, I think the lifetime of the B field is longer enough. If this is longer than the relaxation time of the induced current, so this incomplete electromagnetic response may be disappear.
Okay, I have some comments and questions, but I can wait for another round.
Yeah.
No, just go ahead. We have time.
Well, so the title of your talk is a production of electromagnetic fields in heavy ion collisions, and from my perspective, there's all the charge that participates in the collision contributes to the dynamics of these electromagnetic fields in one way, and then there is this discussion that you propose here, where you are talking about the dynamics of the quarks that are being created by in this particular medium, right?
Yeah, yeah.
And so, given what I understood were your inputs were basically some PDFs or the analogous of a PDF for the CGC,
Mm-hmm.
and some and the up there it says in the Glauber model.
Yeah.
Given those as your inputs, my questions regarding the conclusion dependence on the collision energy of the system and on the approach to calculate electromagnetic fields has to do with the fact that you're looking basically at the, let's say, intrinsic creation of electromagnetic fields due to the dynamics of quark charge appearing in this medium, right? Only. There's no external electromagnetic fields being created by the colliding charge, let's say, part the spectators or anyone else in this approach. Is that correct? Is that a fair statement?
Yeah, I think is correct. You are correct. Yeah.
Thank
you.
Alejandro?
Thanks, Anna. Thank you. This was a very nice and illustrated talk and very well organized. Thank you very much. I have a couple of comments and also questions. First, regarding Malena's question concerning the energy dependence of your conclusions. It appears that RIC and LHC in those regimes, nuclear transparency is an important aspect of any considerations, and therefore I believe that your Boltzmann equation describes that situation. However, if you go down in energy, I think that an important aspect to take into account is nuclear stopping. So because of that, it may be also important to take into account that the lifetime of the system will increase. And as a matter of fact, it increases. When I mean the lifetime, I mean the lifetime of the electromagnetic pulse. So the pulse will be wider in time. And therefore, perhaps there are extra processes, not only gluon or quark dominated processes, but also, in the central region, you may also have proton, that is nucleon interactions in your kernel as the two particles that start the processes. So this is something to take into account. I believe that, yes, there is a strong energy dependence on your statements, and that there is room to understand a bit better this approach to describe the electromagnetic response of the medium. And the medium maybe not just quarks or gluons, QCD, fundamental degrees of freedom. But this is just a comment. My question goes...
okay, I see. Because in the very low cladding energy, there will be, as you said, the proton and the neutrons in the central region, and their evolution should be also included in the...
Right, especially at low energy. So I believe that part of the message here is that with these discussions is that perhaps you would also like to think about this regime. But
yeah. For the energy we consider here until the 200 GeV of anti-HC energy. So in the central region, our assumption is right. Yeah, because
I agree. Except perhaps, and this is just a small comment, and I'll go back to my question. There is also another important ingredient that you may be missing, and it's the fact that the larger the energy in the collision, you also generate vorticity. So vortical motion also contributes to the possibility to increase the magnetic field. And this is going to be even more important at lower energies. Not only because there is high energy involved in the processes, but because of this vertical motion, you will have valence quarks, so to speak, going around. In any case, that's just a comment, and it's a nice calculation. I like it a lot.
Yeah, you are very is right. Yeah, in a very low collating energy, there will be, as you said, the vorticity will generate. Right. This vorticity may be also,
and moreover, there will be less transverse expansion. So you see, it's a very delicate interplay to study in more details the electromagnetic response of your medium, and the medium has to be defined according to the colliding energy. So you have to be careful there, I guess. But then my questions. I understand that you focus on the production of electromagnetic response, and for that I understand that what you're saying is what is the kind of magnetic field or electromagnetic field, to be more precise, produced by these processes which you are describing in terms of this Boltzmann transport, and then you're concluding that there is an incomplete electromagnetic response due to the fact that the relaxation time is not large enough compared to the lifetime of the system. So the medium is not going to be able to react and to produce a magnetic field. So I think this is a relatively fair assessment of your nice discussion. However, I just wanted to bring out to you another point, which is very important, I believe, and this concerns the pre-equilibrium stage, which, as you mentioned, contains, because of your arguments, basically the magnetic field from vacuum, right?
Yeah.
Which may be very large if you take into account the magnetic field produced by the spectator, so to speak, especially at large energies. So one has to keep in mind that these very strong magnetic fields, even if they are produced in the absence of quarks, as you rightly pointed out, in other words, not real charges present, basically, in your approach, they can influence virtual quarks. As you actually showed, your distribution functions are gluon-dominated, and basically this is C-quark dominated as well. So you see, if you have processes in which you want to produce electromagnetic fields, photons, for instance, or even virtual photons that will eventually decay in something else, shape, size, or whatever, you have to keep in mind that these processes can be induced by magnetic fields when you have virtual quarks, not necessarily real quarks. So, for instance, consider you have a couple of gluons that come together and they fuse, and they produce you a photon. This process is forbidden in vacuum. It's three vectors in one vertex. This is not allowed. But if you have the presence of a magnetic field, then this is allowed. It's not forbidden anymore, and therefore you can create a lot of photons if you fuse a couple of gluons. And the same is true if you study the decay of a gluon into a photon and a gluon, these kind of processes. So we cannot take back home the message that even in the pre-equilibrium stage, the production of these electromagnetic photons, either real or virtual, is
okay. What I mean is the photon produced the QQ bar. Like in
that case, yes, but in the case in which you have two gluons producing a photon through this triangle process, in which you have only virtual gluons, that is not suppressed because these are virtual photons. Quarks, virtual quarks, and therefore they are not subject to your considerations from my point of view. So in other words, it's a very nice work, but I believe the message is not that clear-cut regarding the production of probes, electromagnetic probes, and one of them can be photons, either virtual or real. So nice talk, but I don't know if you have any comment on this question.
Okay, thank you for your very nice comments. Yeah, and I want to ask is, does the photon? I think the photon process, maybe the cross section is much smaller than the gluon to QQ bar. So does
well,
it?
There is again, it's a competition. It's especially in this pre-equilibrium stage, you know that you're gluon-dominated, as you showed in your this plot that you're showing. You have to divide the gluon density by 10 so that you have something to show in the scale that you're showing for the other. So you're gluon-dominated. So even though you may be suppressed by factors of the electromagnetic coupling when you produce photons, you have a lot of gluons, and that more than compensates for the cross section. If you wish, eventually we can share with you some papers that we have to show that is the case. But in any case, what the message here is that you have lots of gluons, and with virtual processes you can produce, taking advantage of these many gluons, a lot of photons. Well, a lot, sizable amount.
Okay, that's really a good idea. I will check that, and yeah, thank you. Yeah, let me write down this.
Okay, thank you, Alejandro. More questions? So just, continuing the question from Alejandro, let's say, in your calculation, is it possible to include new processes like the one Alejandro is saying? So to calculate the cross-section of this of this process and estimate if it can increase this response?
Yes, it's possible. If we have the cross section, I can sample the photons and the next and to do the but we need to treat that as unshared particles.
So let's say we give you the cross section, you can include it in your simulation.
Yeah, you're right.
Okay, nice.
Because the Boltzmann equation just you just give the cross sections and then you can involve them in the whole space. And
okay, thank you. So more questions? No, if not, let's thank the speaker again.
Thank you.
Okay, I'll now stop recording.
Yeah.